In this, the final lecture in this course, we speculate about life as computation. In astrobiology, we've always been tethered by biology, our form of life. But what if we go beyond this assumption and step far outside the box and consider the possibility of life without biology or life after biology? That's what we're going to do now. Our entire discussion of life has been based on the one planet we know that has life and the history of that life over 4 billion years. We will try and search for biosignatures for that form of life, and we'll try and search for the technology that our civilization has developed in counterpart on other planets. This narrows the scope of our search for extraterrestrial intelligence, and it gives a focus to the activity. But what can we learn by stepping out of the box and being a bit more broad with how we consider intelligence and life itself? One of the co-discoverers of DNA, James Watson, was interviewed by a New York Times journalist soon after the discovery. He was asked about the meaning of his discovery, and he said something striking. He said that life is digital information. Now think of that. That was in 1950. When, again, computers were the size of a family home and not in everyone's pocket. He was recognizing that although DNA and RNA are specific molecules where information is coded in the form and shape of amino acids and proteins, that there was nothing particular to that. The general mechanism of life might in fact be coding digital information. So the question arises, is biological life as we understand it the only way to achieve the attributes of life that we think are essential? There's a field of study that is a bit of a niche, interdisciplinary in nature, and not entirely reputable because some of the wild ideas that appear there, called artificial life. It's been around since the 1970s, since computers began to get powerful enough to do experiments and digital simulations. This emerging field is characterized by several things, and it involves different types of scientists doing this work. It involves theoretical biology, which is the idea that the biology that we have on this planet need not be the only way biology is structured or organized or occurs. So exploring possible or potential biologies is an interesting thing to do. It involves the idea of artificial life, which isn't to say unreal life. It just means new ways of defining what life is that are not specifically tethered to the way it developed on this one planet. It involves the idea of bottom-up, not top-down. In other words, what are the various ways of generating complexity, since life obviously is complex, from simple parts? It involves synthesis, not analysis, where the outcomes are not described and prescribed a priori. It also leverages interesting ideas in biology like emergence. Emergence is the idea that life is not necessarily the sum of its parts, and that when you get sufficient complexity, new qualities and attributes emerge that could not have been predicted in a deductive way from the simple components. In other words, it goes beyond a reductionist idea of biology. And finally, it gives centrality to the idea of computation. The idea that the computation that life's processes occur on Earth could be analog or literal and could occur in very different ways. So artificial life research and its cousin, artificial intelligence, which is making heavy progress in the current era, have several agendas. One is to gain a deeper understanding of our biology. The other is to understand how strange biology might be in other examples. And the third is to explore the role of pure computation as a basis for life and intelligence. Some of this work started decades ago, when you could make simple systems, computational systems, in this case, a cellular automata. What we're looking at is a simple system where cells have an on or an off state, digital, ones and zeros, and where the rules for how a cell turns black or white are set by very simple patterns in each direction. Even with simple rules and a single starting point, complex patterns are generated. And after many iterations, some of these patterns are not simply predictable from the initial conditions. Cellular automata and other computational machines have led to the fact that complexity can emerge from simple conditions, just as our form of complex biology emerged from simple conditions. The end point of these arguments is a provocative argument put out by philosophers a decade or so ago, and it's called the simulation argument. In the simulation argument, based entirely on probability theory and logic, and not really referring to physics or biology at all, one or more of the following propositions must be true. 1, the chances that a species at our level of development can avoid going extinct before technological maturity are negligibly small. So let's see what we mean by some of these terms. In the simulation argument, technological maturity is defined to be a state of a civilization where they can reproduce entities like themselves purely digitally, computationally, artificial life essentially. That's technological maturity. And we might argue that we're within sight of that, with our computers and our brains replicated with computer technology, artificial intelligence, that at some point it might be independent of real brains and real biology. So the first premise is that the chances that a species can avoid going extinct before being mature are negligibly small. In other words, you never get to that point. The second possibility is that almost no technologically mature civilizations are interested in simulating minds and biologies like ours. In other words, they could do it, but they choose not to. It's not one of their activities. It's not interesting to them for some reason. The third possibility, remarkably, is that this has happened and you're actually living in a simulation. Let's look at some possibilities within this provocative argument. One possibility is if increasingly advanced technologies make civilization unstable, we and others like us may destroy ourselves before we gain this amazing capability. That's a sobering possibility that we have to take seriously because of our own difficult history with technology, where for everything like an iPhone, there's something like a nuclear bomb that could destroy us many times over. A second possibility is that it requires convergence among all these sufficiently advanced civilizations for none of them to engage in the activity of creating simulated entities like us. This seems implausible because if you look at our world, we obviously put a lot of effort in technology and recreation into creating video worlds of greater and greater verisimilitude. In other words, we're creating virtual worlds that are increasingly indistinguishable from the real world. So we are doing this activity, making it better and better. Suppose one is false, then a significant fraction of species at our level of development become technologically mature, and so are able to create entities like us. Suppose 2 is also false, then at least some of these mature civilizations will use their resources to run computer simulations of minds like ours. The other thing to bear in mind is that as opposed to creating biological creatures, which requires materials and energy, creating technological simulations of creatures like us is computationally cheap. The power of computation increasing according to Moore's law means that there's almost no energetic resource required to create simulated entities like us. So the logic here is provocative, because if 1 and 2 are false, then all we're left with is the third possibility, the simulation hypothesis itself, saying that we are simulated entities of some superior intelligent civilization. Remember, it's not logically coherent to reject all 3 possibilities. You have to pick your poison. There will be an astronomical number of simulated entities and minds like ours because it's so cheap to make them, vastly more than the number of organic brains and bodies and biologies. So by the principle of mediocrity, you probably do have a simulated mind. Let me summarize this argument. As weird as it sounds, it's logically airtight. The simulation hypothesis says that for every non-virtual early 21st century human life, there are many more subjectively indistinguishable or broadly similar virtual lives. Now, this is a weird argument because it assumes substrate independence. It assumes that you can have intelligence without biology. It assumes you can have life without biology, in silicon if you like, where non-carbon-based life forms are possible. And what we think of as consciousness is possible and can be recreated computationally. Now, most people reject this argument intuitively, Your conviction that your life is non-virtual, of course, is no better founded than anyone else's. Because if the simulation hypothesis is true, then the odds of your life being non-virtual are low. And so while everyone believes their own lives to be real or non-virtual, they're all wrong if the simulation hypothesis is correct. Philosophers have even written esoteric papers on how you should behave if you think you live in a simulation. And they've argued, interestingly, that there is some logic philosophically for obeying a golden rule and not simply being nihilistic or chaotic in your behavior. You might, however, want to act interesting in the simulation so as not to be written out of the next version. So, this is obviously not a completely serious argument. It's designed to elucidate the intriguing possibility of what might happen if there's post-biological intelligence in the universe. Is this implausible? Not really, if we look at advance of the computation in the last century, and especially in the last few decades. The concept in computation is called an ancestor simulation. Once again, we're assuming substrate independence, and so that the brain can just be perceived of as an electrochemical network that can be recreated as easily in a computer as in an actual brain. An ancestor simulation, then, is a simulation of the entire mental history of all humans that have ever lived. And if you just crunch the numbers of the typical operations per brain per second and the number of humans that have ever lived on the planet, the number of computer operations or digital operations required for one ancestor simulation is at the high end about 10 to the power 32. That's an incredible number of simulation operations or computations. But actually, if you project computers into the future, it's only about 50 or 60 years away if Moore's law continues at its current rate. So there's an assumption here, which is that computational intelligence will supersede biological intelligence. The question, the intriguing question from astrobiology is, has this happened elsewhere in the universe, since it potentially could happen on this planet, the only one we know of where there's intelligent life? So what is the role of post-biology in the universe? We've got to the shimmering edge of our subject of astrobiology, to questions that we can't answer now and some that may be unanswerable. But the entire subject is framed in the words of Carl Sagan, because we have the tools now to answer some of these questions. I don't want to believe, I want to know. At the fringe of our subject, we come to the simulation hypothesis. The idea that biology, the path that's taken us to intelligence, communication, possible through space, space travel, and technology that now lets us explore the universe, is not unique to the Earth. Also, that it could be a stage in evolution where eventually biology turns into post-biological entities. The basis of this argument is the belief in the power of computation to mimic the role of biology and intelligence without the presence of biology or actual brains. It's a provocative argument. We have no idea of its truth, although it's logically valid. And we have to ask the question, in general terms, is it possible that biology like ours is just a stage in the evolution of intelligence and life in the universe at large?